Good morning, sir.
Good morning. Actually, there is some problem is there with my laptop. It is continuously restarting. I joined with some another system.
Okay, sir.
Now the problem is I have the don't have the PPT. Have to explain.
Okay, sir. Should I can you send the P yesterday you have sent me the PPT, no, sir? Can I play that PPT, sir? I'll moderate.
Yeah, you can.
The same PPT, sir, which you have sent me yesterday through WhatsApp.
Yeah,
Okay.
that one and actually another is also there, but continuation so that you open it and you
Okay,
share.
sir.
Easy.
I'm opening it, sir.
So webcam is not ready. Board, Microsoft Word board that you can share the
I'm sharing it.
factorial experiments. Yeah,
Uh, which one, sir? I have
factorial,
experimental
factorial,
design PPT, sir.
uh, factorial experiments that I shared to you.
Factorial experiments haven't you haven't shared me that, sir. You have sent just basic principles of experimental designs.
Only two that I shared.
Yes, sir. Yes.
Oh, uh, but actually, that I started the factorial experiments in the
Okay.
last session. That what I have to, not this one. This is already over.
Okay, sir.
Factorial experiments that have to.
I don't have that PPTs.
Okay, no problem. I will explain the concepts and all.
Okay, sir.
Because today that I have to complete the that one and fractional factorial designs also.
Mm.
Okay. Uh, I'm sorry for the inconvenience due to I'm not having the PPT to share to you now right now. Uh, so in the last session that I'd already given on factorial experiments. Okay. The same thing that I will continue for today's session. Generally, the factorial experiment is a factor is a particular force which is changing or varied in the experiment at the will and under the control of the experimenter. So the treatments are somewhat slightly differ with the previous definition of the varietal trials. The combination of two or more levels of more than one factor are said to be treatments in factorial experiments. Let there are two factors A and B, and each factor has two levels. Let's suppose levels are A0 and A1, so low level and high level of A, and B factor is also having two levels, B0 and B1. The combination of two factors at different levels like A0, B0, A0, B1, A1, B0, A1, B1 are said to be the treatments. And the main effects that what I defined based upon the simple effects. The effect of a factor uh, that you are evaluating by changing in response produced by changing the levels of that factor. So this is nothing but the average of the two simple effects in a 2 square factorial, that what I had explained in the last session. Okay. Um, and interaction effect is the difference in the response between the levels of one factor by keeping all the levels of the other factors at fixed levels. So just like in the 2 square, whatever the cross a0 b0 and a1 b1, a1 minus a1 b1 minus a0 b0, that is one simple effect of interaction. And another one, uh, a0 b1 and minus a0 a1 b0. So sum of these two is the total interaction effect, and if you are taking the average of that, that is called an interaction effect. I had already defined the contrast. So contrast generally that what you are defining, a linear combination of K treatment means, let's suppose TIs, and summation of CI TI is said to be a contrast if the summation of the CIs, that means the coefficient values, is equal to 0. And orthogonal contrast means one contrast is said to be an orthogonal to the another one. So both are contrasts only, and the uh, cross product, sum of the cross products of the two contrast coefficients is equal to 0. Summation of some AI BI is equal to 0. And this orthogonal contrast is mainly used whether the factors are independent or not, or contrasts are independent or not. So for that we are going to use this one. And had already given the generally the null hypothesis when you are considering the 2 square factorial experiment. So we are having totally three two main effects. One is effect of factor A, effect of factor B, and interaction effect of AB. Interaction effect means combined of the two factors with both are at high level. So three hypotheses simultaneously that you are testing in the factorial experiments of the 2 square. So main effects and interaction effects. Suppose if it is a 2 cube, so totally how many? So you are having the three factors. So three factor, three main effects, and every pair. So two factor interactions and three factor interactions. So all those that you are going to estimate, and we are going to test it. That means we are testing the null hypothesis that there is no significant effect of the main factor A, main factor B, main factor C, if there are three factors, and also AB, AC, BC, and ABC. So there are three hypotheses simultaneously that you are going to um, test in the 2 square, and uh, 7 hypotheses simultaneously that you are testing in 2 cube factorial experiment. Suppose if it is 2 to the power of 4, then 15 hypotheses simultaneously that you are going to test. So suppose if it is a 2 to the power of 4, that means there are 4 factors A, B, C, D. Each factor has 2 levels, let's suppose low level and high level. indicated with 0 and 1, then the hypothesis will be the main effects of A, B, C, D. There is no significant differences. So 4 hypotheses. And two-factor interactions also existing. So the two-factor interactions are, we are considering the AB, AC, BC, AD, BD, and CD. So for C2, that is 6 two-factor interactions, and three-factor interactions, ABC, ABD, and BCD, like ACD. So the four three-factor interactions and one four-factor interactions, ABCD. So totally we are testing 4 plus 6 plus 4 plus 1, that is 15, the hypothesis that you are going to test in the 2 to the power of 4 factorial experiment. And generally we are calculating the sum of squares. Suppose if it is a 2 to the power of 3, then you can use the hypothesis that um, if it is a 2 to the power of 3, it is just like a cuboid. So cuboid is containing totally 8 corners. Okay. Suppose if I taken the room of a uh, one room, the corner that you would consider, and there are 3 axes. So one is one side of the corner, and the another side, just like it is in a 3-dimensional object or 3-dimensional geometry, whatever the graph. So x-axis, y-axis, and z-axis. And on the x-axis, y-axis, z-axis, those are the individual effects. And suppose if we are taking the one plane, just like A corner and B corner, so whatever the joining of the top of the another corner, which gives the AB, and similarly AC and AD. Sorry, ABC only. So AB and AC and BC. So 3 corners. And again that you are considering the ABC. So what is the another corner? So totally the 8 corners of a cube that you can identify it. And whatever this also that you are generally indicating with like A0, B0, C0, or A1, uh, um, A1, B0, C0, A0, B1, C0, A1, B1, C0, A0, B0, C1, and A1, B0, C1, A0, B1, C1, and A1, B1, C1. So totally these are 8 possible combinations. And these are also generally are indicating with 1. 1 is nothing but all are at low level, A0, B0, C0, A, which is nothing but A1, B0, C0, and another one is B, only B. That means B is at high level, the other two are at low level, that is A0, B1, C0. And next is some AB. So A and B are both are at high level, there is no C. So A1, B1, C0, and C. So that means there are no A and B. Therefore, A0, B0, C1, and AC. AC is generally indicated with A and C are at high level. A1, C1, but B is 0. And BC is A0, B1, C1. And ABC is A1, B1, C1. Like that is a 2 cube factorial experiment. and this is generally are indicating with 2 to the power of 3 factorial exponent cuboid. And there is another concept of full factorial. These are all full factorial experiments. Now, suppose if I taken a 3 square factorial design. What is a 3 square factorial design is, let there are 2 factors a and b, and each factor has 3 levels, like the levels that I am indicating with 0th level, 1 and 2. Okay, 0, 1 and 2. So 3 levels. Then the corresponding factorial uh, design or experiment is said to be a 3 square factorial design or 3 square factorial experiment. And generally whatever this 0, 1 and 2 are low level, intermediate level and high level. High level is indicated with 2. The treatment combinations, what are the treatments at here? So there are 2 factors A and B, A0, B0, A0, B1, A0, B2 and A1, B0, A1, B1, A1, B2, A2, B0, A2, B1 and A2, B2. So totally you are getting 9. So just like you write a 3 by 3 table for each row that you are indicating with A0, A1, A2 and column that you indicate with B0, B1, B2. So totally the 9 treatment that combination that you can write it. Okay, which is very easy to identify. Now in the 3 square factorial experiments, how to evaluate the simple effects? Because uh, each factor is applied at 3 levels. So low level, intermediate level and high level. Suppose I want to find out the effect of factor A. So factor A is applied at intermediate level and low level. Now you consider A1 level and A0 levels, which are fixed, and whatever the combinations are there, all those that you consider for A1, then you subtract whatever the A0 combination levels. Okay, so that you will get the uh, simple effect of the intermediate to low level. Similarly, that you have to calculate from high level to the intermediate level, A2 minus A1. So two differences that you are calculating at here, A2 minus A1 and A1 minus A0. Also you can calculate A2 minus A0. So here out of these 3 different effects, A1 minus A0 means continuous levels, intermediate to low level differences that I am calculating. This is generally said to be a linear effect. And even if you are calculating A2 minus A1, that is also said to be a linear effect. But suppose if you are calculating the A2 minus A0, that is generally said to be a quadratic effect. It is not a simple effect. So, and what, because high level to very low level that you are calculating in that. And whatever the this levels also that you are writing as AL, AQ. L stands for low and Q stands for quadratic. So whatever AL value is nothing but A2 minus A0. Okay. And whatever the AQ value is, that is quadratic effect of the factor A, is A at high level, that is A2 minus 2 times of A1 plus A naught. So that means A at low level. So you consider the coefficients. The coefficients are 1 minus 2 and 1, the sum value will be 0. So as a result, this is a contrast. Even similarly that you have to calculate for factor B for the low level and also at quadratic effect. So BL is nothing but BL minus B naught, and BQ is nothing but B2 minus 2 times of B1 plus B naught. So which is generally said to be a quadratic effect. Now, then you have to consider the interaction effects. What are the different interaction effects? ALBL, ALBQ, AQBL, AQBQ. So 4 that you are calculating. L stands for linear effect. Q stands for quadratic effect. Okay.
Excuse me,
Now,
sir.
when you are
Excuse me, sir. Sir, can you use whiteboard, sir, in
okay.
this at least? Is
Yeah,
it possible?
whiteboard that I want to place, but it is not installed at here. The whiteboard is not installed, and Wacom is also not installed. That's only the problem, because I'm using suddenly the another
Actually,
system, and
MS
mostly in
Teams.
5 to 10 minutes. Huh?
Uh, okay, sir. MS Teams itself
5
has
to
a
10 minutes,
white.
my system may be ready.
Okay, sir. Okay, sir. Then not an issue.
Yeah.
Thank you, sir.
So if once my system is ready, then I can go for the PPT and also the backup. Okay. Anyhow, that I will try on background that I will try to install.
Okay, sir. Okay. Thank you, sir.
Okay. Because it will waste the lot of time. Okay, that's a notation that all that I will show on the board later. Now I will give the only just concept of the theoretical, just like now concept of the confounding and concept of the fractional factorial that I will explain, and whatever the notational aspect that I will explain in the later. Okay. Uh, Now what is the concept of the confounding? Confounding means because generally confounding concept that you are going to use only in the factorial experiments. Uh, let's suppose if you have taken a 2 to the power of 4 factorial experiment. That means there are 4 factors are there. Each factor has 2 levels. So totally there are 16 treatments that are existing. Now I want to conduct an experiment with 16 factors, 16 treatments. So the accommodating all the 16 is at single time, at single place. The experimental material may not be enough. So in that type of the situations that I am going for stage wise. First time that I am taking one set of values, like out of the 16, I am using 8 at first time. In the next stage that I am going to use 8. That means, so totally 16 are divided into 2 equal parts. This is generally said to be a concept of blocking. So first block 8, second block is containing 8. I am conducting for all the 16, but not at a single time, because the experimental material is not enough. Or I am conducting the experiment first time at one place, or second one at some another place. So then also the experimental material is not homogeneous. Therefore, there is a blocking effect, or experimental material effect is also involved on the treatments. So such a concept, in that type of the situations, one effect you cannot estimate. So that's why it is generally said to be confounding. Confounding is nothing but it is missing. One estimate, one treatment effect that you cannot estimate. Such a concept is called confounding. So why you are not in estimating? Because one effect is coincides with the effect of the blocks. Due to blocking, so some effect will be missing. We cannot estimate. Such a concept is generally said to be confounding. And this is generally what we are going to use in case of whenever you are not in a position to accommodate all the treatments at a time. Now suppose uh, the experiment, the number of factors are more, or the number of levels are more, then we have to go for the blocking concept. But in the confounding concept or blocking concept, even the 2 to the power of 4 or 2 to the power of 5, so 2 to the power of 5 means 32. So 32 treatments that you have to accommodate. So the experimental material may not be enough. It's accommodate for all the treatments at single time. So then I'm splitting, and some at one place and some at another place. So due to that, the soil effect or fertilizer effect, there are some other effects may be involved. So you cannot estimate it. So such a concept is the confounding. But in the all treatment that you are applying, and but you are not in a position to estimate. Now the another concept is, instead of conducting, suppose if it is a 2 to the power of 4, so 16 treatments are there. I am not having the experimental material to accommodate for all the 16. And also the all treatments are also not available. Then I am conducting the experiment with only 8. The other 16, other 8 that I am totally ignoring it and conducting the experiment. So, but I want to estimate, even though the other treatment that are not applied, I want to study the effect of those 8 also. Then how to? So in that type of the cases, generally you are going for fractional factorial designs. So fractional factorial designs, confounding of the factorials, or blocking of the factorials, that is, and full factorials. Full factorial designs that are applied, all treatments you are in a position to conduct all treatments that you can apply at a time. So confounding concept, you are not in a position to accommodate all the treatments. You are splitting some combinations at one time and another combinations at another place or second time or stage wise. Whereas in fractional factorial, out of the total treatments, I am accommodating only, I am conducting the experiment with only few of the treatments. Suppose there are totally 16 treatments are there, but I can accommodate only 4, and my budget is not enough, and only 4 are there out of these 16 treatments. Then you conduct with only these 4. But I want to study the effect of the other one also. Then you have to go for the fractional factorials. So fractional factorial. So 2 to the power of 4, I am conducting with only 4. That is 2 square. That means 1/4 only that I am applying out of the 2 to the power of 4. Okay. So this type of the concept is a fractional factorial. But I am estimating the effect of the other one, and those effects are aliased with the existed ones. So in this one, the which effect that you are not in a position to estimate, that you have to identify and we have to calculate. So that is one of the most important part in the fractional factorials and also in the concept of the confounding. And suppose if it is a fractional factorial design of 2 to the power of half replicate or 1/4 replicate, or it may be some other. Generally, the fractional replication of the factorial experiments are not practically important for few factors, and these are mainly useful in some circumstances, like the factors are all two-factor interactions, that is lower order interactions, and which are interest to study, then you can apply. We are not generally interested to study about a higher order. So that's why even when you are taking the confounding also, the higher order terms may be not estimable, may not be applicable. And the experimental errors are substantial, requiring a relatively large amount of internal replication to provide some satisfactory estimates for the main effects and also two-factor interactions. Those are generally said to be the Elias terms. So generally the concept of resolutions that you are going to use, like resolution 3 designs, resolution 4 designs, and resolution 5 designs. What is resolution 3 designs? Even generally, when you are going for the any of the statistical software, like a design expert, he will ask about whether it is a resolution 3 design or resolution 4 design. What is a resolution 3 design? Resolution 3 designs are uh, no main effects are aliased with any other main effects. That means one main effect is not aliased with another main effect. So, but the main effects may be aliased with two-factor interactions. Like suppose A, B, C, D, 4 factors are there. So A is not aliased with C, or A is not aliased with B, or A is not aliased with D. Aliased is nothing but just like we are calling as with a nickname. So whatever the effect of A is not equal to effect of B, or A effect is not equal to B effect, C effect, or D effect, or B effect is not equal to C or D, or C effect is not equal to D, like that. So one is not, main effect is not aliased with another one. That means no two persons with the same name, just like that one. So just like instead of, suppose aliasing is nothing but A and C are aliased, means A effect is same as it of the B effect. So instead of suppose Bhattacharyalu, so instead of that one NBC that you are calling it. So the name of the person I am calling with a nickname. So these are this is whatever the other name that is generally called an alias. So that concept that what generally are going to use in the fractional factorial designs. Okay.
Sir, I have a doubt here.
Ah,
So, we should not have any alias effect. Am I right?
yeah. Main effect are not aliased with main effect, but main effects may be aliased with two factor. A effect is equal to AB effect.
In that case, how do we interpret the result?
Because AB is you are not in a position to estimate. That's why I'm equating A effect is almost equal to AB effect like that. Okay. So whenever you are not in a position to accommodate all those, so I am conducting with only few and I am trying to guess or estimate the other one based upon estimated one only. So even though that is not estimated, so that effect will be equal to one of these which are estimated. That's why these are called aliases. Are you following or not?
Yeah. Okay.
Suppose if you are having four factors are A, B, C, D. I am conducting with only 8 treatments. Now A is aliased with CD. Means CD interaction effect that you are not in a position to estimate, but the combined effect of CD is equal to the main effect of A only. That what you are saying in the fractional factorial experiments. Okay. And resolution 4 designs are these designs in which no main effect is aliased with any other main effect or two factor interactions. But two factor interactions are aliased with each other. So two factor interactions are aliased with two factor maybe, but which are aliased with some other also. Okay. So no main effect is aliased with any other main effect. And two factor interactions are with higher order or with the same. So that is called resolution 4 designs. And resolution 5 designs are no main effect or two factor interactions is aliased with any other main effect or two factor interaction is aliased with any other main effect or two factor interactions. But two factor interactions are aliased with three factor interactions. Okay. So accept.
Okay.
So two factor interactions are aliased with two factor interactions. So that is generally said to be a resolution 5 designs. Okay. Just you WhatsApp just say a link to our system. These are the resolution 3, resolution 4 and resolution 5 designs. Now suppose if you are taking the half replicate of 2 to the power of 4 of the factorial experiment. So half replicate of 2 to the power of 4 factorial experiment. Now half replicate is nothing but generally are considering the totally 2 to the power of 4 and we are writing symbolically as 2 to the power of 4 minus 1. So that is almost seems to be 2 cube only. That means 8 factors. Whatever the which 8 that combination that you have to consider. So that is one of the most important in this case. So, and how to find out the confounded term, that is also one of the most important aspect. So which effect that you are not interested to study, that only maybe not be estimable. The other must be estimable, so that you have to design it. So which effect that you are not interested? Generally, we are ignoring the higher order terms. So higher order effects are maybe missing. Suppose if it is 4 factors, I am not interested to study or effect of the ABCD, then I am designing with in one block that I'm with the 8 treatment that I'm applying, like all are at low level, A and D are at high level, B and D are at high level, AB are at high level, CD are at high level, AC, BC, and ABCD. Even though the ABCD is applied, but it is not estimable in case of this off replicate. Okay, that's what you have to understand, because I already applied, but why I am not in a position to estimate that particular. So because that effect will be nullified with the block effect. So that is major situation that what you are going to use in the. Now, what are the Elias terms? So Elias terms that you can find out, just you are multiplying. One is multiplied with ABCD, then ABCD that you will get. And AD is multiplied with ABCD. So AD, so BC is Elias with that. So AD and BC, so are equivalent effects. And BD, what is equivalent to that? Now BD that you multiply with ABCD, then whatever the A and C which are left over, therefore AC effect is and BD effect are same. Like that you are going to study it. And we are going to use the fractional factorials. Actually, this concept was introduced by DJ Finney, who is the father of factorial experiments in 1945, when the number of factors are very large, and even the experiment employing a fraction of treatments only and exact fraction only, then only we can go for this fractional replication concept. And all the main effects which are interest to study, but the higher order effects which are not interest to study. Very rarely that you are going for the fractional factorial designs. And most of the other cases that you are going to use, that means because if you are not in a position to accommodate all the treatments and not interested to conduct the experiment with all those, but I want to estimate in those cases only that you are going to study about these factorial experiments. Otherwise, we can we are not giving much importance for this fractional factorials. Generally, the factorial experiments will take a lot of cost because more treatments are there. Even suppose we are having 5 treatment, 5 factors, and each is having the some 3 levels, then 3 to the power of 5. So 3 to the power of 5 is that number of 9 into 9, 81, 81 into 3. So 243 treatment that you have to apply it. So applying of 243 is very difficult. So therefore, we are going for the fractional replications. So which combination that you have to use, that you have to identify it. Even the blocking concept also, whatever the confounding. So in those cases also, which effect is not estimable, and how to find out uh, which is confounded. So that I will explain. So meanwhile, if you are having any question that you can ask, I will try to, because whatever the split plot designs are also, they comes under the part of the factorial experiments only, but those are asymmetrical factorial designs, because I'm allotting some treatments in the main blocks and some treatments in the subplots. So in those situations, and the number of levels are not equal. So some factors have having high level, some 2 levels or 3 levels, and other factors are having a different number of levels. So which are asymmetrical, not symmetrical. Symmetrical is always L power F. Okay. Is the system is ready? Huh? Oh. So is it give a problem వస్తుంది ఇంకా? Networking problem. Oh. Okay. Now you are having any of the doubts that you ask first, then I will go for, because the most of the cases that you are going to use the response surfaces, which are the most important ones, and also we are analyzing the experiments in most of the chemical technology and pharmaceuticals, central composite designs, and which are almost even the Takuchi designs. Takuchi designs are nothing but just like it is a factorial experiments type. So Taguchi designs are fixed designs. The Taguchi tables are available, and each factor generally you are expressing with the 2 levels, plus and minus. So negative, and that is generally we are using a code. So -1 and +1. So combination of these plus ones and minus ones, that what I'm going to use in the Taguchi designs. And Taguchi tables that are available for different type of the number of factors. These are mostly just like seems to be an Hadamard matrices. I think you have anybody heard about Hadamard matrices? So Hadamard matrices are nothing but containing the matrix with only plus or minus ones, either +1 or -1. If you are taking any of the cross product of any two rows or columns, sum of any two rows and columns cross product will be 0, such that the Taguchi designs were constructed. Suppose if you are taking the 4 by 4 table, first row you write all plus ones. Next row you write 1, -1, 1, -1. And third row you write -1, +1, -1, +1. And fourth row -1, +1, -1, +1. And if you are taking the any of the uh, two columns, so the sum of the cross product will be nullified, 0 that you will get. So such a designs are generally said to be Hadamard matrix. You can also search in Google search Hadamard matrices of order 4. So you can get the Hadamard matrix. And such a type of the designs are the Taguchi designs. And these Taguchi designs are mostly that you are going to use in the planning of the experiment for response surfaces. Let's suppose there are three factors are there. Each factor is having two levels, and I want to estimate the response, and I'm constructing one design with these plus or minus ones. So for that cases, either Taguchi designs, or you can also use central composite design. So even central composite design is also same. Suppose you are having three factors. You write a design with totally 2 to the power of 3 points. That is just like a factorial points. 1, 1, 1. 1, 1, minus 1. 1, minus 1, plus 1. 1, minus 1, minus 1. And similarly, the another 4 rows with that you write repeat by taking the first column as minus ones. So totally we are getting 8 points. These are called the factorial points. Next we are taking the axial points. Axial points are plus or minus a 0 0, 0 plus or minus a 0, and 0 0 plus or minus a. And some central point that you are taking with all values as zeros only. So such a design is generally said to be a central composite design. So all are plus or minus ones with a 2 to the power of 3 factorial points and 6 axial points and 1 central point with all zeros. So such a design is generally said to be a central composite design, which is mainly used in the response surfaces. So you can see many of the talks or many of the experiments, most of the pharmaceutical cases, we are going to use these central composite designs. Okay. And based upon the central composite design that you can estimate the response value by fitting a model. So here we are generally are going for fitting of a regression model, like either it may be a first order model or it may be a second order model. If it is a first order model with three factors, y is equal to beta naught plus, which is a constant term, beta 1 x1 plus beta 2 x2 plus beta 3 x3. So that is called a linear response surface model. And there are three factors. Then you can use whatever the central composite design for that. Suppose if it is a second order model. So in the second order model is beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 11 x1 square beta 22 x2 square beta 33 x3 square plus beta 12 x1 x2 plus beta 13 x1 x3 plus beta 23 x2 x3. So that means single terms, square terms, and cross product terms. So with that you are totally writing the 8. So such is generally said to be a second order response surface model. Okay. That what generally are going to use in model fitting for the based upon central composite. You can also use rotatable designs. So in the rotatable designs, generally said to be whatever this plus or minus a any value, but instead of that, the value will be fixed with root 2. Because some of them they came to me for specifying some particular design. Uh, uh, for the 3-factor in some one of the factorial central composite design in some chemical industry or some pharmaceutical experiments. In that cases that had given some designs in when the microbiology and genetics, they're also mostly they are going to use these response surfaces. At that means at which point that you have to collect the reading. That is one of the most important part they are going to consider. So that I will explain now. So almost the system is ready. Now I will explain with another one. Okay. Please try to accept the admit the another one. You are getting the yeah. Sir, please. I'm shifting to another system. Please admit, sir.
Just a second, sir. Wait for a moment. How to make it bigger? Yeah, we have admitted you, sir. Just check once.
Okay.
We don't have another laptop. Okay, okay.
Okay. Hello.
Yes, sir.
Okay. Uh, share just sir. Please allow the sharing, please. Give the access for sharing.
Yeah, just now I gave, sir. You can try once.
Yeah. Okay. Is it the screen is visible now?
Yes, sir. Yes. We can see, sir.
Yeah. Let's suppose x1, x2, and x3 are three factors. And now, if I am going to use y is equal to some beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. So this is generally said to be a linear response surface model. This is generally what you are going to use for analyzing the experiments. And I am taking the whatever this x1, x2, and x3, the three factors, I am taking at different levels. So let's suppose I am using the 1, 1, and -1. Let's suppose this is a temperature is one factor, and this is some pressure that I am applying, and this is some another one that whatever that you are factor that you are going to use. So temperature, I'm using at a two temperature. This is maybe time factor also that you can consider. Now the temperature that I'm using two levels. Let's suppose 20 degrees centigrade and 40 degrees centigrade. And so that is I'm indicating with 1, and 30 degrees centigrade is nothing but the 0th level, and this is -1, and 40 degrees is +1. So these are the coded values. And pressure, I'm using how much pressure that you are applying. Let's suppose at 3 levels. So that is also I'm indicating with -1, 0, and +1. Let's suppose if it is pressure that I'm applying is with 100 or some 40 or 50. This is 150. So whatever this pressure of HP that what you are going to use, that you can time that I'm using. So time may be I'm using 20 minutes time or 1 day time uh, and 1 hour time, and another is some 100 minutes. So equi 11, then this is indicated with 0, this is -1, and this is indicated with +1. So like the coded values that I'm going to use. Now 1, 1, 1. This is +1, let's suppose, and this is -1, and 1, 1, and this is also uh, sorry +1, and this is -1. 1, -1, -1. Okay. So and similarly now I'm repeating the same. Uh, uh, so here I am writing the another 4 combination also. Uh, -1, 1, 1, and -1, 1, -1, and -1, -1, +1, and -1, -1, -1. So, so totally you are having 8 points. 1, 2, 3, 4, 5, 6, 7, 8. So this is a 2 to the power of 8 factorial experiment. So this combination that what I am going to use. That means we are conducting the experiment with the 3 factors. So one is the temperature that I'm using, pressure that I'm using, and time that I'm using it. So temperature, what is the combination at whatever that you are having? 20 degrees centigrade and 50 with the pressure, and with 20 with 20 minutes time that I taken the reading. So that is the 8th combination. Suppose if I'm using 40 degrees centigrade, okay, and whatever the uh, this value is 0 degrees 100 pressure and 60, then whatever this combination will be also coming, so that I will argument. These are only the factorial points. And if I'm argumenting some more points, like uh, some 1, 0, 0. Okay, or you can also write all are zeros. Okay, 1, 0, 0, or some a 0, 0, minus 1, 0, 0, and plus 1, 0, 1, 0, and the another one, the combination 0, minus 1, 0, and 0, 0, plus 1, and 0, 0, minus 1. So whatever these 6 points are called generally axial points, and this is called a central point. And whatever this total design is said to be a central composite design. So which is mostly that you are going to use in most of the uh, industries. That means at which point that you have to consider. So please confine to this factorial experiment. Okay. So this is the total design that what I placed it. So 8 points and one central point, and the other points are, so this is the ninth one is central point, sorry, central point, and other are axial points. So totally, if you are having the k factors, 2 to the power of k factorial points and 2k axial points, and at central point only one point that you can take, or some number at the same degree. I'm taking the 3 replications, so same measurement at same pressure, same temperature, and same time, that I'm taking the 3 or 4 times reading. So replication it may be. So even in these cases also replication may be. But all at all points they must be existing. Then only you can analyze the experiment by using a central composite design. Suppose if I have conducted the experiment and collected the reading at this particular combination and this combination, the other are not I collected the reading, then you cannot carry out the analysis. So designing of the experiment is the most important one. So what combination at which combinations that you have to collect the readings, that is most important in this part. So otherwise the total experiment, even if you are taking at one point, if you have not collected the reading, the total will be wasted. So even the other point that you have collected, it will be wasted. So that is a better result that you can find out. You can estimate, but it is not that much of accurate. There is some the cross product terms and other terms will exist. So we are generally trying to nullify those. Okay, and you can check it once in this one. If you are taken in this particular design, whatever this combination is multiplied with this combination corresponding 1 plus 1 into 1, 1, and 1 into 1, 1, and 1 into minus 1, so minus 1, and 1 into minus 1, minus 1, and minus 1 into 1, minus 1, and minus 1 into 1, that is minus 1, and minus 1 into minus 1, plus 1, and minus 1 into minus 1, plus 1. So exactly that value will be 0. So this is the generally what type of the design that what you are going to. Even if you are taking the first column and third column, so that value will be 0. And second column and third column, that value will be also 0. This is almost the Taguchi designs. Okay. So just you are going to use our plus or minus ones. And you are constructing such that whenever you are writing the covariance matrix, these are some of the square terms diagonally you will get. In the off diagonal elements, you will get zeros. So off diagonal elements or zeros is nothing but the factors are independent. So it is not, one is not influencing the other one. So that is what it is indicating. So this type of the design that what you have to use it. So which are the most important in the most of the pharmaceutical and chemical industries. So mostly they are going to use either response surface design, first order model or second order model. Suppose if it is a second order model, the model will be like this. Suppose if there are only two factors, y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus some constant beta 11 x1 square plus beta 22 x2 square plus beta 12 x1 x2. So this is said to be a second order response surface model. And generally we are going to fit based upon this design. Once the experiment is conducted, I am trying to estimate these constant values. Okay, even if you are given whatever the other temperature values, like whatever the coded values it may be also. So some minus 0.1 and 0.3 and 0.2. At this point, what will be the response that you can estimate based upon this model fitting? So for that particular purpose, you are going to use these response surface models. What will be the estimated response at a particular points or at particular levels or combinations or the coded values. Suppose I had not collected the reading even at 15 degrees temperature or 35 degrees temperature. But also you can guess it based upon fitting of the model. So first you have to estimate the model. So for this, how to estimate the parameters? So beta hat generally are estimating based upon the simple this. So x dash x inverse x dash y. So whatever this x matrix and you transpose it and multiply with the same, you will get a 3 by 3 matrix and multiply with x transpose and the responses. So you will get a vector of the values beta 1, beta 2. So all these values that you can find out. So once the beta values are these values are estimated, then if you are substituting the x1, x2 values, so x1 value and x2 values are known. X1 square, x1, whatever the value is there, the same value that you are squaring it, and the cross product that you are calculating. So you can estimate it. So this is a very useful designs which are having the functional relationship, and we can estimate the responses, and also you can carry out the regression analysis. So whatever the analysis, whether the model is fitted or not, that you are writing. The source of variation, uh, uh, lack of fit of the model. So whatever the model is due to regression, generally are writing it. Sorry, due to model error, and also total. And whatever the sum of squares that you are calculating and degrees of freedom and
P.
and mean square value, and also that you can calculate the another row, another column with okay. Undo. Now the sum of squares values that you have to enter at here. Um, okay, and this is the total sum of squares and error sum of squares and degrees of freedom that you are calculating based upon the number of parameters in the model minus 1, and total number of responses observations minus 1 and n minus k, and mean square value that you are calculating sum of squares value by its degrees of freedom. And similarly, whatever this value by n minus k, you will get the mean square, and whatever the mean square value by the error mean square value, you will get the variance ratio. This is the analysis of variance that what you are calculating for the response surface design model, which is mostly that you are going to use in industry. Okay. The another one is what I explained in the previous. We'll share the uh, even the factorial experiment I had not shown it because we maybe some odd it seems to be like if it is a 2 to the power of 3 factorial experiment, and generally you are having there are two levels are A, B, C. These are the three factors. Each factor is having two levels, 0 and 1. Okay. Now the combinations that what you are having is A0, B0, C0. It is generally indicated with normal, and A0, B, A is 1 with B0, C0. This is generally indicated with A, and A1, B1, C0. This is indicated with AB, and A0, B1, C0. This is indicated with B, like this. Okay. Whenever it is high level that you are indicating, otherwise we are not indicating it. Just 1 minute. Hello. Sorry for disturbance. Now here I'm going to conduct the experiment. Suppose this is a totally experimental material. I'm allocating all treatments um, okay, 4. So 4 and 3, let's suppose here I'm conducting with 1 A, AB, and B. Okay, and also that if you are going to apply the another C, AC, ABC, and if there are only 2 are there, if it is 2 square, let's suppose you consider this one. And second replicate, this is a replicate 1 that you can consider, and replicate 2, replicate 3, replicate 4. Okay, and if it is a 2 cube, totally the 8 that you have to write it here. Okay, this is corresponding to 2 square factorial experiment. And 2 to the power of 3 factorial experiment, you are writing 1 A, sorry, here I'm A and B, AB, C, AC, BC, and ABC. And totally this 8 that you have to write. Suppose if it is a confounding cases. So if it is a 2 to the power of 3 factorial experiment, but if it is a confounding case, I'm conducting the experiment with, this is one block, which you can accommodate only one A, B, AB. And here I'm taking the another block. So remaining C, AC, BC, ABC. So this is at one place. This is called block 1. This is called block 2. So in this type of the design, I am applying all the 8, but not at one place. So this is called confounding. Confounding, or called blocking concept. And in this case, one effect you cannot estimate, even though that you are conducting the experiment with all. So here depends upon the cases which one that you cannot estimate. So here ABC is not estimable. And suppose if you are conducting the experiment with, I'm not conducting the experiment with all this, only with this one. Then I want to study the effect of this also. Then you have to go for the fractional factorials. So in the fractional factorial, 1 is multiplied with a C, so a C only. And A is multiplied with a C, that is AC. And B is multiplied with suppose with a C, that is BC. So that I have written at here these treatments. Now suppose ABC is confounded, and these are the treatments which are directly conducted the experiment. Then 1 is multiplied with ABC, ABC. That means all one effect will be same as that of ABC, and A is multiplied with ABC, so you are getting the value is BC. So A square that is nullified, so you are getting BC only. And B is multiplied with ABC, you are getting the value as AC. That means A effect is equivalent to BC effect. B effect is equivalent to AC effect. And whatever the AB is multiplied with ABC, then you are getting C. So whatever the AB effect is equivalent to C effect. So this uh, one is said to be aliased with ABC. A is aliased with BC. B is aliased with AC. And AB is aliased with C. So this is the concept that what you are going to use in the fractional factorials. So if the main effect is not aliased with another main effect, then it is generally said to be resolution 3 design. And two-factor interactions, no main effect is aliased with the main effect, and main effect is aliased with the two-factor interactions. Main effect means single. So in the resolution 3 designs, no main effect is aliased with the main effect. Main effect may be aliased with the two-factor interactions. So in that case, it is said to be resolution 3 designs. And main effect are aliased with the two-factor interactions, and two-factor interactions are aliased with either two-factor or higher. Then it is generally said to be a resolution 4 design. And resolution 5 designs are main effects are aliased with two-factor, two-factor are aliased with either three-factor, and three-factor are aliased with either three-factor or higher. So then it is said to be a resolution 5 design. Okay. So that means here, if I estimated the effect of A, its alias term is BC. Therefore, the estimated value of A is equivalent to estimated value of BC. That directly you are saying in the fractional factorial designs. Even the effect of B is equal to AC. That's what you are going to explain directly in this one. Now there is another concept of the factorial designs. Let's suppose we are having in the confounding, we are having two types. One is generally said to be total confounding, and other one is said to be partial confounding. So total confounding is, I here suppose if it is a 2 to the power of 2 factorial experiment. So 2 to the power of 2 means I am taking the only two blocks. Now here 1 A, B, A, B. So this is block 1 and this is block 2. So totally this is said to be one replicate. So replicated 2 is also same. This is replicate 2. Okay. So whatever the treatments are applied in previously in first replicate in the block 1, the same treatment that are applied in second replicate also, in block 2 also, the same treatments, then it is generally said to be total confounding. That means one estimate is not applicable. Instead of that, suppose if I'm applying one at here, A, B, and here, instead of A, here B and here A. Then in one replicate, one combination in one block, but in another replication, I'm taking another combination of the treatments. Then it is generally said to be partial confounding. Okay. So I think you are following what is a total confounding and partial confounding. Okay. If you are applying a different combination, then it is partial confounding. So in what is the advantage of the partial confounding is in total confounding, say a same combination if you are applying, one estimate is not up, one treatment combination you cannot estimate. The same also you cannot estimate in the from the another replication also. But once that you are repeating, what is the advantage? So if you are changing the combination, even though that you are not estimating the effect of AB at here, but you can estimate at here B, but you cannot estimate the another one, which is already you are studying from the previous one. So that is the advantage of the partial confounding. And there is another concept called balanced confounding. So balanced confounding is here, suppose whatever the same interaction effect, let's suppose if it is a 2 to the power of 3 factorial experiment. In first replicate, second replicate, third replicate, the 3 replication that I mean. In first replicate, the block 1 and block 2, let's suppose AB is confounded. In second replicate, let's suppose AC is confounded. That means we cannot estimate. And in third replicate, BC is confounded. So 3 replications, and only these are the 3 two-factor interactions that are existing. All that you are going to use, therefore it is said to be a balanced confounding. So instead of that, if you are writing AB is confounded, AB is confounded, AB is confounded, in all the 3 replications, it is a total confounding. And instead of that, if I'm using AB is confounded and AC is confounded and AB is confounded, this is said to be a partial confounding. So you can identify what is the difference between the total confounding, balanced confounding, and partial confounding. Okay. And in confounding, all the treatment that you are applying, but not in the same blocks. Suppose if you are applying all the same, all 4 in a single block, like 1, A, B, AB, then it is said to be a full factorial. This is a confounding or blocking concept. And instead of that, I'm applying only with 2, like I'm applying only A and B, not applied all at low level or all are at high level. Then it is generally said to be fractional factorial. So fractional factorial, this is a 2 square factorial experiment of fraction. So that is half of 2 square. Generally, the same thing you are indicating with like this. 2 to the power of 2 minus 1. We are not subtracting and writing 2 power 1. Okay. Simply are writing. This is generally writing 2 power k minus 1. This minus 1 is indicating how much fraction that you are. 2 power minus 2 means 1/4, 1/4 of 2 to the power of k. That generally are indicating with like this. Okay. 1/4 replicate. This is generally called. And 1/3. So 1/3 of the generally that concept that you are going to use in the 3 square factorial experiments, because it may not be exactly divisible. Therefore, we are using a fraction is with the same part. Okay. So this also you can write as 3 power k minus 1. Just like it is also 1/3 replication, but it is half part only, that what you are treating it, but less than the half, not exactly the half. Okay, a suitable fraction that you are considering it. So these are the various concepts that what you are going to use, and so if you are having any of the doubts, that I will clarify one by one. And also that had given the low level and high level of 3 square factorials. Generally, I had given AL and BL. Both are the linear effects. So linear effect and AL BQ and AQ BL and AQ BQ. So whatever the linear effect, so that what you are calculating, and the quadratic effect, that what you are calculating. Linear effect, the value that what you are calculating, which is always in the linear form. So quadratic effect is always this is generally A2 effect minus A0 effect. And if it is a quadratic, generally you are writing A2 minus 2 times of A1 plus A0. This is generally said to be a quadratic effect, how we are calculating. Okay. And whatever this, similarly, even for BL and BQ also. So replace A with B's, then you can find out. And whatever the ALBL effect, that is nothing but whatever the A2 minus A0 into B2 minus B0. Okay, just like the same that what I'm, even I am not writing the brackets, that to consider it. Okay, this. Similarly, AL minus B, AL into BQ, AL and B2 minus B0 into sorry, A2 minus A0 into B2 minus 2 BA1 plus this one, and coefficient is 1 minus 2 and plus 1. So the value will be 0. Therefore, it is a contrast. Here coefficient is plus 1. Here coefficient is minus 1. The value will be 0. Therefore, it is a contrast. Okay. Generally, we are calculating the sum of squares value is always that you are calculating all these 4 that you have to add it. So you will get the sum of squares of AB. So SS due to AB is nothing but sum of these 4. Okay. So this is what we are going to use in the 3 square factorial experiment. And the 3 square factorial experiment design generally we are showing in a 3 by 3 table. So here factor A at a 0th level, 1 level and 2 level, and factor B at a 0 level, 1 level and 2 level. So whatever the combination A0, B0, A0, B1, A0, B2, and A1, B0, A1, B1, and A1, B2, A2, B0, A2, B1, and A2, B2. So whatever the sum values that you are calculating for rho, which is the effect of A0 and A2 and A1, and B0, B1 and B2. So those that you are calculating and you are going to use in this one. Okay. So any of the doubts that you can ask now. because the factorial experiment is somewhat complicated when you are going through it. But the mostly that you are going to these factorial experiments in the case of the response surfaces, and mostly response surface designs that you are going to use for conducting the experiments and for also analyzing it. And for that you can use the SPSS for the analysis, which is very easy when rather than the design expert, because in the design expert there are many combinations that are more complicated actually when you're comparing with SPSS software, because SPSS is simply how to enter the data if you are knowing analyzing buttons that you have to press it. But whereas in the design expert it is not that much of easy. Okay. Actually that I downloaded, but it is not totally is working, enterprise version. Okay. So please ask if you are having any other doubts.
Sir, so when we should go for augmentation of the results?
Augmentation of?
Augmentation means when I can increase the number of designs.
Yeah, when you have to go for the augmentation. Okay. Now, just I will show. Now, initially that I conducted with the 3 factors. Okay. There are 3 factors are there: x1, x2, x3 to correct the readings. I conducted the experiment with just like with a 3 square factor, 2 cube factorial experiment, 1, 1, 1, and 1 minus 1, and 1, 1 minus 1, and 1, and 1 minus 1 minus 1, and minus 1, 1, 1, and minus 1, 1, minus 1, and minus 1, minus 1, 1, minus 1, minus 1, minus 1. So my budget is enough for only up to 8 points conducting the experiment. Now I suppose if I want to augment, so some more observations also that I want to collect it, at which point that you have to collect. Then take axial points only. Axial points are, so you have to consider plus or minus A. A may be some particular value. This is generally what you are considering is root 2, 1.414, 0, 0, and minus root 2, 0, 0, and 0, root 2, 0, and 0 minus root 2, 0. And similarly, you conduct the experiment with the 0, 0, root 2, and 0, 0 minus root 2. So these are the augmented points. Some more point that I want to augment, which does not affect the previous one, and also possible to estimate at 0 point that you consider it. So these are called augmented points. Okay. Augment means additional point that you are taking it. So which it does not affect for the model, and which is very easy to estimate. Such points only that you have to consider. Even if you are taking some other point, there is no problem, but it should not be a problem of estimation, because already that you have conducted with a systematically at these points. Suppose if I conducted with a root 2, 3, and 2 like this, then estimation is very difficult. So estimation is very easy if you are collecting the augmented points are like this. Okay. Am I touched the whatever the road that you have clarified that you raised it?
Yes, yes, sir. Yes, sir. So we should take care to see that whatever the points we augment, it will not affect the estimation.
Yes. So it is very easy to estimate the model by using the model.
Oh, okay. Oh, right. So this
So
is
generally
only
we are,
possible with central composite design.
yeah, central
Right, sir?
composite designs. Yes.
Yeah. It is only seen with central composite, not with
Yes.
placket Berman or not with box metal.
Uh-huh. Placket and Burman is also constructed. Placket and Burman designs are with only factorial points.
Okay.
Placket and Burman. So all are factorial points only. You check it once in the Placket and
Yeah.
Burman designs.
Yeah,
The tables are there with
yeah.
plus or minus ones.
Yeah, yeah, yes, sir, yes, sir. Even the
So
same case with box Benkan also,
yeah,
it will be
uh,
plus or minus only.
yes.
One more doubt I have, sir. Say,
Mm,
okay, I have conducted my experiment with the two cube, that is two level, three
mm,
factors, okay?
okay,
But
okay.
whatever the experiment I have conducted, I say that maybe I had some data which is not correct,
Mm,
okay?
mm.
Then I want to increase the number of experiments here.
Okay.
How I
Yeah.
should increase the number of experiments? What is the level, even the data, the statistics
No,
will tell
at each
me
point
the
that you take
two.
two readings. At
Okay,
each point you take two readings.
at each point.
At each point that you take two readings or three readings.
Yes, we will take Nasir when the design, when the
But all
experiment.
points must consider.
Okay, all points must consider. Yes, you are right. Say,
Hmm.
for example, there is some linearity in the data is missing. Okay,
Hmm.
but still, I have conducted the experiment. I have conducted the experiment with effect of temperature, with effect of pressure and time upon my
Okay.
release of drug, say, for example. But whatever the results I plotted, and when I subjected the data to the
Okay.
ANOVA, the result is not giving a correct one. Same, it is not following the such a poly quadratic or whatever the linear. Okay,
Hmm.
that means the data is not significant.
Hmm.
Is significant. So
Okay.
I want to increase the number of experiments there itself.
No need to increase, madam.
Sir.
Now, generally, first we are fitting the model with linear model
Okay.
and testing the lack of fit of the model.
Yes, we will test the lack
Uh,
of it. Yes.
so lack of it. So that data is not follow. Suppose the hypothesis is rejected. That means it
Yeah.
is not following a normal. Then
Okay.
next step is what you have to do. You have to increase the level. So next we are going for the second order model.
Okay. Increase the level. Okay.
Yeah.
We should go
So
second order.
generally, so if it is not following a linear, then it will follows. Just I'm checking the curvy type. That is called
Okay.
second order quadratic parabola.
Okay,
So
sir.
again, I tested the lack of it. Let's suppose again it is not fitted.
Yes.
Okay. Then go for the third order.
Okay.
So then the curve type this. And next we are going for the polynomial, higher degrees that you are
Higher
taking.
order.
Yeah.
Yeah.
At some place it will be fitted
Okay. Okay.
because all possible curves that will set at it.
Okay.
So, but generally you are searching, this is the order. First linear, next second order, third order, and so on. So if it is then generally you are going for the exponential fittings.
Yeah.
So exponential fittings are Gombrich curves so that you are going to fit.
Okay.
But generally linear or first order and second order, mostly it will fit.
Yeah. Okay. Okay, sir. Thank you.
Any questions?
any more queries, participant? Okay. Thank you all the participants, and thank you, sir, for your valuable lecture. And Archana ma'am, Associate HOD of our department, is going to give vote of thanks. Ma'am, please come.
Hello everyone. I am very glad to propose this vote of thanks. So first of all, I thank Dr. Bhattacharyalu and Malaya sir for taking their time out and conducting this FDP, and especially in when they have their personal commitments as well. And I thank you all the lively participants for your feedback as well as questions. Finally, I would like to appreciate and congratulate the coordinators of our department, Mr. Sai Siddharth and Pavani, for their hard work in making this FDP successful. So thank you one and all.
Thank you, madam. Thank you for giving an opportunity.
It's our pleasure.
Thank you, sir. I'm Siddharth, coordinator of this event. This lecture was very helpful for us even in our research projects. Actually, the factorial design and ANOVA are probably the key elements for us to design how an experiment has to be conducted. And especially the software of design of experiments have given a very good input into us, mostly the hands-on session that probably, I mean, we mostly doesn't know how to operate the design of experiments of software, but that has given us very good insight. Thank you so much for your valuable input, sir.
Thank you, sir. Thank you for giving, and sorry for the problem with the system. That it is not working in time. Okay. Sorry for inconvenience.
No problem, sir. Yes, sir. Thank you, participants. You were very good actually as a participants. I would appreciate your valuable questions and valuable inputs.
Thank you very much.
Thank you, sir. I am leaving.
And sir, you have given very good, nice presentation, taking this to all the levels. Can you please provide us your email ID, sir, so that if at all I have any doubts, I can get back to you. Because presently I'm working at university, sir, and of course I'm a student of Usmania University. I did my PhD in the Department of Technology.
Under whom?
Professor Amareshwar, sir.
Huh?
Professor Amareshwar, sir. Panuganti Amareshwar, sir.
Okay. Amareshwar.
Yes. Yes, sir.
Dwarakbhat@rediffmail.com.
Okay.
Yeah. Dwarakbhat.
Sir, can you text that in the chat box, or if possible? I will paste them in the WhatsApp group as well. In the chat box.
Okay. Either dwarakbhat@rediffmail.com or usmania.ac.in. Okay. Is it visible to all of you?
Yes. Anyway, I will post this in the WhatsApp group and chat box as well. So not an issue. I have your email ID, sir. No problem. I'll post.
Yeah, I will type on the chat box also.